Hi there, folks. Today we're looking at density curves and normal distribution. And so for starters, the density curves really just shows the distribution of data by showing it its area under the curve, okay? It's very similar, and we'll even describe some of these things the same way we described the shape of the data when we were looking at other types of graphs, like when we were looking at dot plots and stem plots, and we talked about the shape of the data, whether it was symmetrical or skewed left, skewed right. The big difference here is I don't have this y-axis that's showing me the actual data values, okay? I'm spreading out the data along a number line and just looking at concentrations of the data, all right? So when we see these large peaks, it just means there's more area under the curve at that peak, which means there's more data values gathered in that area. So instead of looking at this from the perspective of actually counting the data values, we're more looking at it in terms of concentrations. We'll talk about it more in terms of percentages. What percent of the data value is in this area of the data? What percent of the data values are bigger than this value? That kind of thing, okay? And so when we look at density curves, again, we have different ways of describing them, very similar to what we were doing with other types of statistical graphs. But like this first one, we would call a symmetrical density curve. And it's symmetrical because, once again, the peak is in the center. When you look at this thing, if you cut it right down the center, each side is a mirror image of the other, all right? This next one, while being symmetrical from the perspective and from the pure definition of symmetrical, yeah, one side is identical to the other, we would call this one uniform. This has its own special thing. And that's because the height doesn't change. Like, the data is evenly spread across all values. Like, this is showing data values from 2 to 6, and across the data values of 2 to 6, everything's spread out very evenly. As opposed to the first one, where most of the data is in that 4 range. Like if you looked at 3.5 to 4.5, that's where the biggest area under the curve is. So that's where most of the data values tend to be. As you get higher, we can see this thing kind of tapering off. See, there's less data values that are in this 6 to 7 range, okay? Because the area tapers off. It's saying, hey, the concentration is starting to fade, all right? And that's what density curves show us. If we look at the next one, again, this is just like when we were talking about this with other things, this one is called skewed right. And the reason for that, again, the peak is off to the left. Yeah, we get that, but because we have all those data values trailing off to the right, the peak, yes, is at the left, but the mean is going to be to the right of where that peak is, okay? So we just say this one is skewed right based on where the mean is in comparison to that peak, okay? And of course, this last one is skewed left for similar reasons. When we look at this thing, yes, the peak is off to the right, but because that those data values, there's more data concentration kind of peeling off and trailing off to the left, it's going to draw that mean value to the left of the peak. So here's the way we kind of talk about these things. A lot of times we'll talk about the concentration in terms of percent of data, okay? What percent of the data would we say is from this value to this value, all right? So in this one, we're going to start with a uniform one because they're really easy to calculate, a simple division. So it says find each value based on the density curve. Well, so with a uniform one, again, simple division because all the pieces as we look at this thing are going to be the same. It's evenly spread. So what percent of the data is above 4? Well, when we look at this thing, let me draw a little dotted line at 4. Well, we just say, well, this area is the same as this area, which means half of it is over here, so 50%, okay? So 50% of the data would be above 4. If we look at the next one, it says, what percent of the data is below 5? So this time we might need to cut this into more pieces. And so if I say below 5, again, because it's uniform, I can easily cut these into equal parts. When we look at these, each of those parts is identical. In other words, when we look at this, because it's uniform, this is 25% of the data, a fourth of it. This is a fourth of that area. This is a fourth of that area. So each of these is 25% of the data. Which means if we're talking about less than 5, so below 5 would be everything from here on over. Well, that's 3 of those 4 pieces. That's 75% of the data. And again, that's really easy because it's uniform, okay? When this gets a little bit tricky is when we're talking about these actual curves where it's not uniform, when we have greater concentrations one place than we do another, okay? And for our purposes right now, we're just going to do some estimation. Let's estimate, what percent of the data would be above 4. And so when you look at this one above 4, when I look at this thing, if I were to draw that, this thing looks fairly symmetrical. Because it's fairly symmetrical, I'm saying that basically I think this area here and this area here are approximately the same. And so if I think those two things are approximately the same, it means that 50% of the data would be greater than 4 and 50% would be below 4. So 50% of the data, okay? Again, that's because this thing looks symmetrical, all right? But look at the next one. It says what percent of that would be below 5. So same question as before, but because this isn't uniform, it kind of makes this a little bit tougher. So when we look at something like this, now I'm talking about, okay, what percent of the area is represented by all of this stuff right here? What would we say in terms of, and again, we kind of have to estimate. Like, unlike the last one was 75%. This one, I'd say that's more than 75% of the total area. I'd say it's maybe closer to like 80, 85. Maybe I'd say, I don't know, let's be real specific as if we could be. I'm going to say it's 84%, because why not, right? So 84%. And you might look at that and go, no, I think it's 83%. Yeah, that sounds like a great estimate, okay? We can see that it looks a little bit more than 3/4 of the total area. So we have to do a little bit of estimation, okay? And that's the deal with these density curves. Now, there is one special type of density curve that we don't necessarily have to estimate on our own. It follows certain percentages. And that's the normal distribution. The normal distribution is essentially a density curve, a very famous density curve that a lot of things naturally fit to, okay? A lot of things naturally fit to the normal distribution curve. And it's just a special distribution curve that kind of has set percentages and set values that it kind of adheres to, all right? So for this thing to be for this density curve to be normal distribution, it has to be symmetrical, so it has to be the symmetric type. It has to have a single peak, and it has to have a bell shape. In fact, all of the curves that have shown you so far, the previous example and the very first example that were symmetrical, look like normal distribution curves, okay? They're not skewed in any way. They're not uniform. They look like that nice bell shape, okay? When something is normally distributed, it conforms to certain percentages, okay? We will find 68% of the data within 1 standard deviation, 95% within 2 standard deviations, and 99.7% within 3 standard deviations, okay? So when I set up a normal distribution curve, we always set it up with the mean in the center, okay? So for this one, the mean would always be the data value. So when we're like writing the values down here, we would put the mean at this middle spot. Okay, and then what we do is we count by standard deviation. So like here, we would add 1 standard deviation and write that value down here. And then we would add another standard deviation. So we'd add 2 standard deviations to the mean and write that value here. And then go 3 standard deviations from the mean, okay, and write that value down here. So those values that were kind of arbitrarily placed in our previous examples are going to be very specific values based on the standard deviation now. Likewise, going the other way, we would go down 1 standard deviation from the mean and write that value here. We would go down 2 standard deviations from the mean and write that value here. We'd go down 3 standard deviations, okay? And again, when we set up a normal distribution curve, yes, we put the mean in the center and we count by standard deviations in order to gather these very special percentages. And so what this is saying, it's basically saying that, hey, in between here, if I were to count all the area within 1 standard deviation, in other words, 1 this way and 1 standard deviation this way, that area right here with this little shape, that represents approximately 68% of the data, okay? And that's pretty special that that happens every time we're talking about normal distribution. When we're within 2 standard deviations, in other words, if I take all the area going this way to 2 standard deviations and all the area going this way to 2 standard deviations, so all of this area here, that area should represent approximately 95, so this chunk right here represents 95% of the overall area under the curve, okay? And then if I go 3 standard deviations, so again, expanding this out a little bit more, 3 standard deviations. So this area right here, just gonna, that was a little bit of a miss over here, but that area represents 99.7% of the data. And notice, like, the 68% we started with is included in that 99.7, okay? That 95% is included in the 99.7, all right? So as we go further and further out, we gather more and more of our data values, and it's a very specific percentage, okay? Here's how we apply that. All right, so something like heights. Heights are almost always normally distributed unless we did something crazy and did, like, a couple kindergartners in a class with a couple ninth graders in a class with, a couple toddlers. You know what I mean? Like, if we were looking at a group of all ninth graders, we're going to find normally distributed data, okay? So height is one of those things that's normally distributed. And so when we look at this, the first thing I'm going to do is I'm going to draw a normal distribution curve, okay? And we know it's normally distributed for this example because, well, it literally says so, okay? It says the height of a group is normally distributed. So the first thing I do is I draw a normal distribution curve. I draw a nice bell-shaped curve, okay? I do the best that I can, and I put the mean in the center. And so this one, it says we have a mean of 5 foot 9 inches, with a standard deviation of 6 inches. And I always count, 3 standard deviations in each direction. You can write them up top or you can write them down here, all right? But if I continue to go standard deviations away from the mean, it means I just add 6 inches each time. So here, if I add 6 inches, that's going to bring me to 6 foot 3 inches. And then if I add 6 more inches, I'm at 6 foot 9 inches. And if I add 3 more inches, I'm at 7 foot 3 inches, okay? Likewise, going the other way, if I'm, again, counting by standard deviations, I'm going to go 3 in each direction, so let's go 3 this way. Well, now I'm counting by standard deviation, so I subtract 6, so 5 foot 3 inches. And then 4 foot 9 inches. And then 4 foot 3 inches. Okay? In other words, this is what this distribution looks like. And now that I have that drawn, it's asking me, well, what percent of the population is over 6 foot 9 inches tall? In other words, what percent of the population is in this area under the curve? Okay? Oh, and I should have like a bottom line to kind of cap this thing off. All right, and all we do is use the fact that this has that 68, 95, 99.7 rule, the empirical rule, but also the fact that this thing is symmetrical. Like if I said, hey, what percent is above 5 foot 9 inches? Because this is symmetrical, that's got to be 50%, okay? So we're using 2 things. We're using symmetry and the 68, the 95, and the 99.7. And so one of the things we know from our 95 is that right here, when I look at the data within 2 standard deviations, in other words, this area right here, we know that this area right here, if I trace that thing really well, we know that that area is 95% of the data, which means if that's 95% of the data, there's only 5% left. In other words, these 2 sections, this little bit that's over here and this little bit that's over here, have to represent 5% of the data because everything in between those 2 values is 95%. Everything outside those values has to be a total of 5%. And now we use the idea of symmetry. If we know this thing is symmetrical, those 2 little pieces, we call them tails on each end, is 5%. Well, if they're symmetrical, each of them has to be half of that. Each one has to be 2.5%, okay? And so that's the idea behind the empirical rule. If this thing is symmetrical and we follow those 3 percentages, we can find any value in terms of the percent of data under that or above or below any value on this curve, okay? And so this one, 2.5%. And again, that's because, state it one more time, in the middle is 95%. What's left is 5%. It's got to be 2.5 here and 2.5 here to give us 100% of the data, okay? That's the idea behind this thing, okay? If I look at the next one, let me clear out some of this stuff. So it says, we want to know what percent of is going to be between the 6 foot 3 inches and the 4 foot 9 inches. And so this time we're kind of putting ourselves in the middle of all this stuff. So the 4 foot 9 inches is right here, and the 6'3" is right here. So we want to know what percent of the data is this right here. And there's lots of ways we can kind of approach this. Let me box that thing off. Okay, so that's the area we're looking for. Lots of ways we can approach this. Like we have a chunk of this thing. Like we know that right here between this value and this value, that's one standard deviation. That's 68% of the data. Okay, which now means we just need to know, well, what's this little piece right here? Okay, and one of the ways we can do that is using our 95 rule. Okay, we know that 95% of the data would be from here to here. So then if we subtract the 68 from that, right, because we've already accounted for that in between there, all right, so you do the 95 minus the 68, it means that those two little pieces have to be a total of 27%. In other words, this piece over here that I'm looking for and this piece, that has to total to 27% because I have to have a total of 95%, and I know the two pieces in the middle total of 68%. Which now means if I use some symmetry, if those two pieces have to add up to 27%, these two little pieces, this piece and this piece, if those have to add up to 27%, it means that each of them has to be half of that, has to be 13.5%, okay? So again, this little piece that we were questioning, that has to be 13.5%. Which means the total area that I have is the 68 plus the 13.5. That's going to be 81.5%. And, this can become a little bit confusing as we're looking at all those little pieces. But again, there's lots of ways to approach this. I could also do it this way. I could say, hey, you know what? If I know that those pieces, just to show you some variety here, if I know that these middle pieces within one standard deviation, in other words, from here to here, if that's 68%, it means that each of these has to be 34%. So this has got to be 34%, right? Well, now I can kind of do what I did before and say, hey, you know what? From here on over, right, that's 50% of the data. And we already figured from our last example right here, this guy, we know that this piece is 2.5%. So now if I take the 50 minus the 2.5%, I know that this piece, everything in between here, this section, has to be 47.5%. And now I can take that 47.5% plus the 34%, I'm back to that 81.5%. So again, it looks like a mess as we start to kind of get into this thing a little bit as we're shading different regions, but it's simply using those values and using symmetry to come up with these little pieces, okay? And in terms of the math that we do as we approach this thing, it's really just a matter of addition, subtraction, and sometimes dividing by 2, okay? So let's try another example. Right here, a class's scores are normally distributed with a mean of 78 and a standard deviation of 4.5. So once again, I'm going to draw the normal distribution curve. I put the mean at the center. So this one's going to have a 78 right in the middle. I'll do this one at the top this time. I like drawing them at the top. So 78 in the middle, and then I add 4.5s, so it's 82.5, and then add another 4.5 to get me 87, and then add another 4.5 to get me the 91.5, and then going the other way, I subtract 4.5, so I'm at 73.5, and subtract another 4.5, that gives me a 69, and subtract another 4.5, that gives me a 64.5. And so again, I go 3 standard deviations in each direction. Let me put a bottom on this thing. And now it says what percent of students scored between a 73.5 and an 87. So once again, I'm looking at 73.5. Oh, I put a 72 there. That's my mistake. This one should be a 73.5. So between a 73.5 and an 87, well, that's this right here. I want to know what that area is, okay? And again, I can approach it a lot of different ways, but a lot of times I'll do this. I'll say, okay, well, I know from here to here is 95, but that's too much. I have to take this guy away. Well, I also know that from here to here is 68. So the 95 minus the 68 is the 27, which means this piece right here has got to be half of that, 13.5%. Okay? So instead of being at 95, I subtract the 13.5%. I'm at 81.5 again. And that's the other thing that you'll notice is you'll see a lot of these percentages used over and over and over again because we're locked into certain percentages. Okay? The next one says, how many students scored below average? And that's a much easier question than you might think. Remember, average is the center. That's what anchors this thing in the middle. In other words, the average is 78%. So I want to know what percentage scored below average. Well, again, this is just simple symmetry. This doesn't use the 68, 95, 99.7 at all. It just uses the fact that this thing is symmetrical, which means 78 is in the middle, which means to the left or the right, that's 50% of the data. Okay? So again, normal distribution curves have these special percentages, but we're just trying to determine, well, what percent of the data is located for this area, all right? We use a little bit of symmetry, and we use the empirical rule.